Okay, let me get started now. So first of all, I guess today is the day the homework 3 was due. That was on graph algorithms. Any questions there people need to know now, or that's turned in? The good thing about turning in homework 3 today is that homework 4 comes out today too. And but this is actually an interesting homework that we're going to. This is the unit on the kind of the programming contest on backtracking, which is what I'm going to talk about today. Any questions in particular? Okay, the first thing I'd like to do before I get to backtracking is get to the problem of the day, which is, I will say, an unusually interesting problem. But I want people to see if anyone thought about this. Okay, so let's just see what the interesting means. Hard at this point, but there's some ideas here that are interesting. The problem is you're given a graph, a weighted graph, and you've got two vertices and an integer k, and you want to find the shortest path from vertices v to vertex w using exactly k edges. Okay, so you can imagine a world where this is like finding the shortest path. Each time you change an edge on if we had a graph, if we had a network, you could imagine if you have a path like this, every time you change edges, it's like a turn. One way to think about this is a problem of, if I'm going to want to find the shortest path from S to T, I want to use exactly k turns, or k minus 1 turns. Does everybody get that idea? So if I only wanted to minimize the number of turns, what would be the algorithm that I would use? If I wanted to find the shortest path from from v to w, where I minimize the number of turns I make on the graph, on the path, what would that be? What would my algorithm be? Breadth first search. Does everybody agree? I want to minimize the number of edges I use. Breadth first search would be it. What if I didn't care about how many turns I made? I'm happy to do this. Okay? Provided I just get the shortest path. What would be the right way to do that? What was that? What algorithm should I use? Yeah? Dijkstra. Dijkstra is how it's pronounced, or at least how I pronounce it. So yeah, you would use Dijkstra's shortest path algorithm to find the shortest thing in the world. But notice that this is going to be asking for a path where we're interested in two things. Given that we're going to use k edges, we want to find the shortest possible path with that constraint. Any questions about this problem? Any ideas on how you can solve it? And if anybody had any ideas, yeah?
What I do is like you start at S and then you find all of the path that has k edges, and then you just pick which one ends at T, and then you also keep track of the minimum cost.
Okay, so one algorithm that you're saying is go and find all possible paths of k edges between U and W. Okay? And the good thing with that, and then you're going to take the cheapest cost one. The good thing about that is correct. What is the bad thing about that? It could be very slow. How slow could it be? It's clear it could be exponential. In fact, we're going to live with that world. But let's imagine a world where my graph looked like this. How many paths are there from S to T using exactly 6 edges? At every one of these things, you can either go up or down. Does everybody kind of see that? So if I want, as I increase the length of k, the number of paths certainly can grow exponentially. It's certainly the number of paths from me to u of length k certainly grows at least as something like 2 to the k. It's exponential in k. And it can actually be much worse than this. Okay? So that would be a correct algorithm. You'll actually see how you would construct all the paths when we finish talking about backtracking today, in this unit. Any other ideas how you could do it? Okay? Let me show you 2 different ideas as to how to do this that will lead to different things we're going to talk about in the future. Okay? The first one that I would like to do is say, what if, let's say, what if I design a new graph such that running Dijkstra's algorithm on this graph will give me the right answer? Okay? Is there a way I can take the data, the input graph, and build another graph such that it will, that the shortest path will have exactly the right number of edges? Okay? What if I take my input graph G, let me do this on a blackboard, just because I feel it gets messy a little bit. What if I have a graph like this? Let's say that this is S, this is T. Let's say I'm going to have A and B. Let's make it a directed graph just for the sake of it. Okay, whatever. Let's say I'm going to make it like this. Okay, and let's say the weights here are, I don't know, 1, 2, 3, 4, and 5, just for the sake of it. Let's say I want to know what is the cheapest way to get from S to T using 3 edges. Okay? Is it possible to get from S to T using 3 edges? Ka-chunk, ka-chunk, ka-chunk. Right? How would I find the shortest path, such path? What if I take my graph, and I make a couple of copies of it? How many copies? I'm going to make a total of 4 copies of it. And I'm going to have all edges, instead of going from within a copy, I'm going to make the edges go to the other copy. S goes to there, right? Because this one should be this thing of size 2. Okay? This is going to be, here in my new graph, I've got an S, an A T, and a B. What if I now have it go, so S should go to this, A should go to T. Does everybody see that? B should go to what? B should go to A and also to T. Do you see kind of what I'm doing here? I am going to, wherever there was an edge in the original, I'm going to have the edge point to the next copy instead. Right? I've got a version 0. This is going to be my graph 0, graph 1, graph 2, graph 3. And what is each one going to be? I'm going to copy the edges from one. All the edges are going to go from stage I to stage I plus 1. Do you kind of see what my connections are? How many people, I don't want to draw the whole thing. And I've got the clumsy pens here. I don't even have color, so I'm in. But do people get the idea of what I'm doing? What is interesting about what I'm doing if I started from a directed graph like this? I'm then going to get rid of these edges. These edges shouldn't sit here. But all the edges now, that's going to describe the connections between every such stage, right? What is interesting? First of all, is this graph that I have going to be directed? Yes. Is it going to be a DAG? Can this have cycles in it? Can't have cycles in it. Why not? Yeah? Because every edge is everything is pointing to the one below it. I can't get back. You can go in, but you can never leave, right? You can't go back to where you were. Okay, so this is going to be a dag. And now, what do we want to know? If I want a path from S to T using exactly 3 edges, what do I know? If every edge I'm taking, ka-chunk, moves me to the next graph. Does everybody see that? Ka-chunk, ka-chunk. Every path from S to T is going to be the only paths that are going to be allowed from this vertex to this vertex are going to have exactly 3 edges. Does everybody kind of see that? I'm forcing this by my graph construction. And now, if I have this graph, if I want to find the shortest path from here to here, how do I do it? What do I do to find the shortest path from here to there? Yeah? Just run Dijkstra's algorithm. Does everybody see that? Dijkstra's algorithm for any graph will find you the shortest path, right? Is this a graph? It is indeed a graph, okay? But it's cleverly designed graph. So the only paths from here to here represent I'm traveling on legal edges, because every edge is going to, from stage I to stage I plus 1 is going to correspond to the edge in the original graph. And it's going to get me, and every path is going to take, basically every time I move from one unit to the next, I use exactly one graph. One edge. Does everybody see that the shortest path from here to here is going to use exactly 3 edges? Okay, as a consequence of how I built that graph. And the length of the path that it found is going to correspond to the length of the path in the original graph. Okay? How many people see how this works? A few people. How many people don't see how it works? Okay, a lot of people. Let's try it again. What is the idea? I'm trying to, you're given, remember, as input the graph. You're given the vertices you care about, and you know how long you want the path to. What I want to now do is run a compiler, okay, something that is going to take my graph and my k and build me a graph such that paths of length k represent all the paths of length k are going to be passed between a vertex on the top level and the target vertex on the last level. Okay? Let's make my graph even simpler. Okay? Although maybe too simple. Just that it's easier to draw. Suppose there was an A and B, and this cost 3, and this cost 1. Right? Does everyone agree that's a simple graph? Suppose I want to know the shortest path from A to B using exactly 3 edges. What would that be? It would be A to B, B to A, and then A to B again. Does everybody agree with that? Ka-chunk, 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 3 edges. Right? Now, how can I find that? What if I build 4 copies of this graph? What if I now get rid of these edges? Okay, I think we now know what those edges were. Right, let's just put them, okay, what am I now going to do? This here has weight 3. This here has weight 1. Does everybody agree? This edge from here to here has weight, what was it? Actually, what was it? A to B, it was 3, and then 1 on the way back. From A to B, it should cost 3. From A to B, it should cost 3. From B to A, it should cost 1. Now, if I want to know what is the shortest path of length 3 from A to B, I claim it is exactly the shortest path in this graph between the A on the 0th level and the B on the kth level. Do you see how I manufactured this graph? How many people see how I manufactured the graph? Okay? You could write a program to build those graphs, right? And then does everybody see that if you run Dijkstra's algorithm on it, you get exactly the answer you want? This is a very simple graph. There's not anything Dijkstra doesn't have to work very hard to find the shortest path here, right? But if this was a more complicated graph, it obviously would have many choices. But every path, ka-chunk, 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 has to be of length 3. And Dijkstra will find the smallest one. Any questions about that? This idea of taking your problem and saying it's hard to design a new graph algorithm, maybe I'm better off designing data for an old graph algorithm, is an honorable way to solve problems like that. That's what I did here. Okay? And this kind of approach is something called a reduction, and we will see it when we get to the NP completeness section. This idea of taking data, the input data, and translating it into something so I can run an algorithm I know about. That's a reduction. Any questions about that approach? Okay, it takes some cleverness to see this, but hopefully the great thing about it is my proof is done. Dijkstra came up with the proof of the correctness of this algorithm, not me. Okay? Any questions? Okay? Let me show you one other idea of how you might, and yes? What would be the runtime of it? That's good. Okay? Would it be just Dijkstra? Well, I've got to pay the cost of building this graph, and then I've got to pay the cost of running Dijkstra's algorithm on it. Right? So let's think about that. If my original graph had n vertices and m edges, and I was doing this for a particular value of k, how much time should it take to build this graph? It's probably, presumably, unless you do something dumb programming it, it's linear in the size of the graph, the output graph, right? How many vertices will this graph have? It's going to have bing bing, giant N, k times n vertices. How many edges will this thing have? It's going to have something like km. I'm going to say that with saying I might, again, whether it's k plus 1 times m or k minus 1 times m, I'm ignoring now. Right? Does we agree that's the right order? What is the running time of Dijkstra's algorithm? Does anyone remember what the running time of Dijkstra's algorithm is? N squared. So what would it be? If it is order n squared, what is it going to be? What is the running time of this algorithm? It should be order k squared n squared. Why is that? Recognize that the graph that we're running Dijkstra's algorithm on, is it this puny thing or is it the whole thing? It is the whole thing, right? So does everybody see that this thing is going to be n squared where n is the number of the vertices in the graph we are running it on, if n is big N, chunk chunk, is k times little n, kn squared is k squared n squared. Any questions about the running time here? People see where it came from? Okay. Any questions? Okay. Stare at this for a second before I give you an alternate weird way to solve this problem, just to make sure you've digested that. Any questions? Remember, now let's think back to Floyd's algorithm a little bit. Let me come up with another idea. Remember at the end of class we talked about Floyd's algorithm for shortest path? What was the idea there? If I knew shortest paths with a certain property, maybe I could build on them with a recurrence kind of thing, a recursive kind of an equation, to figure it out. What if I had the following function? Let me call it C of x, y, k, which is going to be the cost of the shortest path from x to y using k edges. Okay? Suppose I had a subroutine, a function that solved this problem, that given a vertex x, a vertex y, and an integer k, told me the length of the shortest path from x to y using k edges. Would that solve this problem? I want to say the answer is yes, okay, because it's exactly the problem, but there may be a reason you're saying no. Why are you saying no? Someone who was saying no. Okay, you might have said no because you're saying, wait, I want the actual path. Let's ignore the actual path. Let's say with dijkstras, we worry about the cost of the path. Okay, once I know how to find the cost, I'll figure out the actual path. Is there a way I can compute this function? This function will tell me exactly what I want to know. Is there a way I can compute that? Well, I'd like to do it recursively using what I have. What do I know? I think I know the following, and let's see if you agree. The shortest path from x to y using k edges is going to be what? I claim it is the min over all v of what? The cost from x to v using k minus 1 edges plus the weight from v to y. Look at that for a second. Okay? This is a recursive thing, right? I am evaluating C by calling C, right? Isn't that a recursive-like thing? That is a recursive-like thing, right? Am I making progress with this? Well, notice that k has gotten smaller, right? What is the shortest path from x to y using 0 edges? Can anybody figure that one out? That's like a base case, isn't it? What is the shortest path from x to y using 0 edges? Someone with a hand? What would it be? I claim it's going to be 0 if x equals y and otherwise infinite. Does everybody see this is an infinity sign? Ooh. Right? What's the way for me to get to Brooklyn? What's the cost of me getting to Brooklyn when I can't drive anywhere? Well, I can never get to Brooklyn, right? Do people see what's going on here? Okay. The basis case you know, there is a recursive idea here where I am solving this thing in terms of smaller versions of the function. And like any other recursive program, if I keep breaking it down smaller and smaller, it will eventually get down to something I can, eat in one swallow, right? Does everybody see that this recursive equation is the right equation? If I'm going to have a path from x to y using k hops, the last hop is going to come from someplace. Where did it come from? Some vertex v. Why v? Well, it minimizes the cost of getting to v in k minus 1 hops plus the cost of the last edge. Okay? I want to minimize that sum, and that's going to be the best v to have chosen. Okay? Any questions about that? How many people sort of see where I might be coming from here? Okay? Any questions? Okay, so this is another algorithm. And this is the kind of algorithm we're going to use with dynamic programming, which is looming a little bit closer on your horizon, but not for the next week or so. Any questions? Any questions about this approach? Okay. One question you might ask is, how fast is this algorithm? Okay. And this is going to be a harder thing to see maybe now, but let me just think about it. How many possible boxes are there here? If we think about how many different values of that function, how many choices are there for x, the start vertex? How many choices are there? N. How many choices are there for the y, which is the end vertex? What? Let's say n. I think I'm going to want this for all pairs. I'm going to need this for all possible pairs, not just my destination. There's n squared pairs. How many choices are there for my path length k? Could be 1, 2, 3, 4, 5 up to k, right? My claim is that there are n squared times k boxes, okay, that have to be filled. And how much time does it take to fill up a box? Well, I've got a loop. This min loop is minimizing what? It's minimizing over n possible choices, right? All choices for that other vertex v. See? Minimize over v. It's going to try all possible v's in that slot. If you think about it, it's going to take order n time per box. The total algorithm is going to be order, I may be rounding it up a little too much, basically this looks to me like an n cubed k squared algorithm. No, take that back. This looks like, let me erase it. This looks like an n cubed times k algorithm. Go away. Uh-oh, it's getting worse. Go away. Okay, any questions about that? Okay, Yes.
Can you go through what you mean by a box?
What's meant by a box? A box is, let's say, how many different subroutine calls are there? You'll see why I call it a box in a week or two. Maybe you don't know why I call it a box. That's fair. But how many different types of subroutine calls are there? If you think of these things, each one of these calls has 3 arguments. The first argument can be any vertex. There's n choice of it. The second choice can have n choices. There's only n choices of that. The third one has only k choices. So there are n squared times k different flavors of subroutine calls. And that's what I'm going to do. And I'm going to store them in a box. That's why I'm calling them boxes. Okay? Any questions? Okay? Yes?
You know, like, I know like when you do analysis, there's sometimes this T of something, like T of something for recursive call. Like,
Okay, so you're saying that, wait a second, what's this recursive calls thing? Let's say I don't want to talk about that now. Okay, we agree that if you had a real recursive thing, it looks like it might be better than this. It's divide and conquer, there's a recurrence. That's something different. Okay, for now I'm happy with the idea that you understand why this is computing what I want it to compute. And if you could get the answer to this in constant time, that it would take, per box, it would take this much time total. That's the second part of the argument. How I do that, maybe I'll tell you in a week or two. Okay? Any questions? Okay, any questions about either of these? Okay, so, you know, if you want to snap a picture, it's not a terrible thing to snap a picture for. I'll even stand here and pose if you want. But, and then we'll move on to backtracking. Okay, I don't know what it is. Okay, go. Okay, good. Okay, what I want to do now is go back to, let me clear this off, and get back to this idea of backtracking. Okay, which seemed, I think I lost my slide is actually part of what's true. Sorry about this, guys. Okay. Okay, let's now talk about a kind of change gears a little bit, although you'll see it's actually conceptually maybe still related to graph algorithms on a way. But I want us to think about a different kind of algorithm problem that many of you have encountered, which is the problem of playing Sudoku. Has anybody, do people still play Sudoku? How many people have done Sudoku? Okay, enough of you to know what's going on. What is Sudoku? Sudoku is this puzzle where you've got a grid of numbers. And your goal is, they give you some numbers, and they give you some rules. They tell you you want to fill in the rest of the grid such that every row has to have the numbers 1 through 9 on there, each one specified once. The column, every column, you have to have the numbers, I guess maybe I'm better off drawing them here. Every column has the numbers 1 through 9 once. 1, 2, 3, 4, 5, 6, 7, 8, 9. Every row has that property. 1, 2, 3, 4, 5, 6, 7, 8, 9. And every box has that property. 1, 2, 3, 4, 5, 6, 7, 8, 9. Any questions about what Sudoku is? Now, those of you who play Sudoku, how do you solve a Sudoku puzzle? You got to fill in those numbers. How do you do it? Does anybody who considers themselves to be, has anybody played it enough to tell me how they play and how they solve a Sudoku problem? There was a time when everyone in my class in the back of my room was doing Sudoku puzzles during class, so that I had good answers then. But how do you go and solve a Sudoku puzzle if you're going to be playing with it? I know some of you have played this thing and have opinions of how you would go about it. You randomly write numbers in every bucket, or how did you do it? Yes, you.
I guess you have like a list of possible numbers that you can put in.
You're saying you look for a list of possible numbers. Let's look for a list of possible numbers. What are the possible numbers in that spot? Okay. Could it be a 1? I don't see any reason it can't be a 1. Can it be a 2? Can't be a 2 because of that. Uh-oh, sorry, I don't know what's happening here. Can it be a 3? No 3. Could it be a 4? Could be a 4. Could it be a 5?
Wait, it can't be a 4.
What?
It cannot be a 4. The box has a 4.
The box has a 4. No 4, right? Could it be a 5? What about anything else? Could it be a 6? Could be a 6. Could it be a 7? No 7. Could it be an 8? Could it be a 9? Okay, so you'd say you're going to go try for every square and find out how many possibilities there are, right? And then what do? Which square looks good to you to fill in? If you have only one item, you're golden, right? Then you can put that one down, right? And maybe that'll help you later on, once you have it down. If you don't have one, what if there's no square where you have one? What do? Give up? What? Guess, and then you say it could be, if let's say there were only 2, you're saying in this case, if I'm determined to put them down here, maybe I temporarily put in a 1 here. And if I then proceed and keep trying to solve it, if I solve it, everything's good. If I find that I get stuck where there's a square that has no possibilities, then I'm in trouble, right? Then I got to roll back all my decisions and try a second possibility. That is the idea of backtracking. And that is going to be kind of this is kind of the motivating example for what we're going to be doing now. How do you search a space of all these huge number of solutions efficiently as you can so you don't do more work than you have to? That is the idea of backtracking. Any questions? Okay. Sorry about this. Boom. So that's basically what we say. We basically are going to use constraints to prune the possible search space. And in fact, Sudoku problems, if you're clever enough about how you prune them, humans can do this without a computer. Okay? Because basically, if you're good enough at solving this exhaustive search, okay, by searching systematically, okay, you can make the search trees for Sudoku small enough that people do it by hand. In general, we have a lot of problems where we might want to solve it by exhaustive search. This gentleman proposed that we solve the problem of the day by exhaustive search. Find all paths of length k. Okay? I had some better ideas, but that's not a terrible idea. It's an idea that gave a correct answer, right? If you wanted to implement that, you need to do backtracking in an efficient way. And backtracking is the idea for that kind of thing. Any questions? So backtracking is, it's a systematic way to get through all possibilities in a search space. And the backtrack algorithm is a general algorithm which you have to customize for your own application. Okay, but the algorithm itself that's really doing the hard part of the work proves to be astonishingly simple. In backtracking, we are going to assume that our solution is a vector. A vector means an array, is a way it's another fancy word for array. An array where the ith element is set from a collection of possibilities. Okay? Let's think back to his problem. He was desperate to find all paths of length k in a graph, k edges. How would we that went from S to T? How could we model such a solution by an array? What should my array have been if I wanted to get such a path? All the vertices on the path. Each edge, let's say I knew I was starting always with S. What do I want? The next vertex is, if my next vertex is A1, that means that my first path edge probably went from S to A1. My second edge went from A1 to A2. How long should this array be? If I'm storing a path of length k, how long should my array be? I am thinking I want it to be something like an array of size k, right? Because it's got to store all the vertices on the path, right? And of course, in the last vertex, if it really is k edges, the last vertex is going to be t, my destination. So in this case, I've got an array of size k. Okay, I will know I have a complete path when the last vertex, the kth vertex is t, and every hop from S to, in general, to the I plus first is going to be an edge in the graph. Any questions? So we want to model our solutions by a vector here. And it's going to, in the case of a path, it's sort of like a permutation. It's an ordered set of the vertices, right? A path is an ordered set of vertices. Bop, 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 bop. If it's a subset problem, maybe I'm going to want to have my vector represent a subset of vertices, I, as being an array of n elements, each of which is either true or false, saying maybe A of I is in the subset, maybe it isn't. Okay? But I'm going to want to represent solutions using this vector. Any questions? Once we've got that under control, then we can look at the backtrack algorithm. The idea of backtracking is I'm going to start with a current partially filled array. My solution is an array. At the beginning, it's not completely filled. What I'm going to do is take my current state of my array and then extend it by making it longer. I'm going to make it longer by adding another element at the end of it. And then I'm going to ask, is what I have now a legal solution? If that's the answer I want, that's great, let's print it out. If not, I'm going to ask myself, can I extend it again in a legal way towards something? If I can extend it, and there's no contradiction with it, go and extend it. If not, I'll try another candidate for this position. And when there's no candidates, that meant I made my mistake earlier, and I'm going to backtrack and change an earlier value in my element. Okay? That's kind of the idea with backtracking. I'm going to start from a place, I'm going to keep exploring out. Okay? Once I get into trouble, if there's no way to legally extend it towards a solution, I'm going to say I must have made a mistake. I'll take the last thing off my solution and try again with something else. Any questions? Okay, good. What does that mean? Sorry about this. Boom, boom. Here is the pseudocode for backtrack. Okay? And this is, I will show you, is almost the entire backtracking algorithm. What is it going to do? Basically, I've got a partial solution and a number of slots in that array that are filled in so far. If what I have so far is the solution I want, my partial solution is, in fact, I can tell is exactly what I want, print it, do with it, send off bells, you have your solution. Otherwise, what am I going to do? I am now going to think about the k plus first position, the next slot in my array. I've got these things filled. The k plus first slot is the first that is empty. I'm going to ask myself, what candidates, what possible vertices or things could go into that slot, given what I have so far? Once I have my set of candidates, what am I going to do? I am now going to try them one by one. I got a while loop. Basically, it could be a for loop for each candidate. Stick it in to that new spot. Decrease it from the set of untried candidates. And now do backtrack. Maybe with this other recursive call. See, there's a recursive call going on. Okay? Once I put this thing in, okay, I now have a bigger array. I'm now going to go look ahead. Maybe this is a solution. Okay? But eventually this recursive call is going to bomb out, and I'm back in this loop, and I'll try the other candidates for the kth position. And once this is done, I will bomb out of this recursive thing, and I'm back to a higher level of recursion, where I'm going to now try a different possibility for an earlier thing. Any questions about this? Yes?
Where are you removing it if that path is not good?
Where am I removing it? Okay, you're saying, what you're telling me is, I put things down, vertex 1, vertex 2, vertex 3, vertex 4. Oops, I think 4 is a mistake. Do I need to erase it? And the answer is no. Because all of you know that if you just, what I need to do is to say, there are only 3 things in my array, right? If you have an array, let's say you're maintaining an array of things. What did you have? You had a counter that told you what the count was, right? If I delete this thing, what did I actually do to delete it from an array? All I did was bop my counter to 1 less, right? It's still there, but it's dead to me. And that's exactly what I'm doing here. Okay? Any questions? Okay? Any questions about this? Let me show you the code for this, because this is now, you're saying, oh, it's pseudocode, you can do anything you want with pseudocode. Boom. This is C code for an even slightly fancier version of backtracking. Okay? What is it doing? It's recursive. Backtrack calls backtrack, right? And what is the reading of this thing? If my current vector is a solution, if it's what I'm looking for, then do what you want to do with that solution once you have it. Maybe you want to print it out. Maybe you want to count it up. Maybe you want to ring some kind of a bell. Okay? In general, if it's not a solution yet, what are you going to do? You're going to construct say, let's make my array larger, and let's consider all possible candidates for this new position. Okay? I'm going to want to grow it. What are the possible choices I might have for the next position? That's construct candidates. And then what am I doing? I have a loop going around for every one of my candidates. What am I going to do? I'm going to copy the ith candidate into the kth slot, that new slot in the array. I am going to forget about make move and unmake move now. Usually they're empty routines, but they give me the ability to do something here if I want. The real thing that I'm going to be doing is calling backtrack. And that is going to come back and test if what I have just built up is a solution. If it is, fine. If not, keep growing. If I get as far as trying all my candidates and I have not found anything I want, I will hit the end of this recursive routine. And it will be finished, and it will go back to the earlier recursive call for it, which had a smaller value of k. Notice that k got incremented before I had called backtrack. When I bomb back, it's to a smaller thing. Okay? Any questions about this? The key to doing it is if you're going to use backtrack on your code for your problem, you need to be able to parameterize. You need to come up with, for your problem, what is a solution, what is process solution, what is construct candidates. And this backtrack procedure will then go through and systematically deal with all the things there. Any questions about that? Okay. Any questions? Does this look familiar? Okay. Does this remind you of anything? Have you ever seen a piece of code in your life before that looked like this? Okay. Yeah? Depth first search. How does it look like depth first search? Well, there is a recursive call, ka-chunk, ka-chunk, within a loop where you're checking through all possible outgoing edges of something. That's what it was with depth first search. Okay? This really is, in some sense, just depth first search on a graph of states and possibilities. Okay? So if you think that out in the universe, there is a graph where there is a node for every one of your possible solutions and partial solutions. If you want to try to find all possible paths of length k like you did, you would love it if there was a kind of graph out there that had all paths of length 1, 2, 3, 4, k, systematically ordered. And then you would just do a depth first traversal over it and you'd visit every one of them. That is exactly what backtracking is doing. Okay? If you understood depth first search, you understand what it's doing. If you don't understand depth first search, well, it's a good chance to come and understand depth first search better again. Okay? Any questions about that? And again, what's the idea? We're getting correctness because we're trying all possibilities, just like depth first search visited all nodes because it tried every possible outgoing edge from anything it discovered. And in order to be efficient, we want to, just like depth first search, not visit anything, more than once, okay? But more to the point, if we know that something is not going to be part of the vertices that we care about, we don't want to look at it. That's really where pruning comes in. Any questions? So you are going to, for homework 4, each of you individually is going to be writing a backtracking program. You can use this recursive implementation, that's fine. To make your problem work, you're going to give it, write your own is a solution, process solution, and construct candidates to do what you want. Okay, that's the key idea here. So let's look at some examples of problems that you can solve in backtracking by going through what those functions do. What does is a solution do? Is a solution is a Boolean function. The output is yes or no, it's a solution. And it's going to tell us whether or not the first k elements of vector A is a solution for what I want. He wanted all paths a path of length k. How do I know it is some big K? Okay, let's call it capital K. It's a slightly different thing. How do we know if our array is right now contains a path of length k? Well, it better be the case that the number of elements in my array is equal to the length of what I wanted. Okay, if so, I've got a path of the right length. If it's less than that, it's too short and I can grow it. If it's bigger than that, something's wrong because I should never have been searching. If I was interested in a path of length 3, there's no reason why I ever should have visited a vertex, a state that was a path of length 4. Right? Okay. The second candidate, which is our function, which is the one that is where you'll be spending most of your time and cleverness, okay, is construct candidates. Construct candidates says, given that I have an array where I filled in the first k slots, little k slots, A1, A2, ... AK, what are the possible choices for the next slot? Okay? If we were doing this thing where we were finding all possible paths of length k, what are the choices for the next slot here in my array? Given that let me use a different notation because it's a little confused. Let's say it's A of C here. Suppose I have filled the first C elements of my array with a path of length C. What is the choice that I have? What are the possible choices for the C plus first element of that array? Okay, I want to construct all paths of length k. I have filled in A1, A2, ... AC. Those are vertices, right? What are the choices for the C plus first position? Somebody with a hand, preferably? Yeah? Would it be n choices? Well, is it true that I can go from this vertex AC to any of the n possible vertices? Oh, why don't I instead say any if this is my vertex A of C, any neighbor of it is a possible choice for the next spot, right? So that's what I'm going to do. I'm going to have you say the degree of this vertex number of choices, and they're going to correspond to exactly the vertices I can reach in one hop from here. Any questions about that? Now, if you try all n possibilities, what would you have had? Well, most of those things wouldn't be real paths, right? They'd be hopping over things that aren't edges. Maybe in is it a solution, you'd check that, but you're potentially doing a lot of extra work, right? What if it was a situation like this where kabunk, 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 there was only one path, right? You would instead say try all n possibilities here and all n possibilities here. Being efficient means use only the possibilities that will lead me to a solution. Okay? That's an important point. Any questions? What is the other remaining part of this? Process solution is easy. Once we know that the first k elements of vector A represent something you care about, what should you do? Well, you may want to print it out. You may want to, whatever the goal of what you did, usually you constructed it for a reason. Process solution is implement that reason. Okay? Any questions? Okay? And so when you do your backtracking program, basically what you're going to be doing is coming up with the implementations of these three functions to parameterize our backtrack search and make it do the right thing. Any questions? Okay. How can we construct all subsets of n things? Okay? First of all, how many subsets of n things are there? How many subsets are there of the numbers 1 through 3? Okay? How many subsets? Yeah? 8. What are they? Well, there's the subset with 1 in it, 2 in it, 3 in it. 1, 2, 2, 3. 1, 3. 1, 2, 3. That's 7. Which one am I forgotten? Empty set. Does everybody agree there's 8 of them? Okay. How can we represent a subset as one of these solution vectors? Okay. There are a couple of different choices you might make. I'm going to represent it by an array of, if I have n items, an array of length n, where every element is either true or false. Suppose, let's say, this looks like if n is 5. Suppose I say true, false, false, true, true. What subset is that going to be? Well, a true is going to mean that the item is in the subset, and a false means the item isn't, right? How many subsets of the numbers 1 through, what subset of the numbers 1 through 5 is represented by this solution? I claim that that is 1, 4, 5, right? Because that's the indices of these things. You kind of see that? What would the vector be that corresponded to the empty set? What would that look like? False, false, false. What would the one be that has all the items in it? True, 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 true. Does everybody see that there are 2 to the n different subsets, and there's 2 to the n different patterns of this type? Okay? If I construct all patterns of this type, I have constructed all possible subsets of something. Any questions? So how do I implement this to construct all subsets? And I encourage you to pay attention to this because the simplest version of your program is going to be exactly this. Okay? What do I need to do? Okay. Let me just look at it. What is my solution going to be? When do I have a solution? I have a solution when, if I want a subset of size n, I filled all n slots with trues and falses. If k is the value of what is the, if k is the value of how many slots are filled in the array, once I have filled it with up to n slots, then I have a solution. What are my candidates for the next position? Well, at every spot it's either a true or a false, right? So this procedure is simply filling an array, telling me the first possible candidate is true, the second possible candidate is false, and that there's a total of 2 candidates. Does everybody agree that that gives me the set of possible candidates for the next spot? This is a very simple case, right? And what am I going to do to print the subsets out? Well, you probably don't want them printed out as true falses. You probably want it printed out as 1, 4, 5. What am I going to do? Well, this is going to print it out. Given the k spots in my array, if a sub I is true, print out element I. Element I is in my subset if a sub I is equal to true. Okay? And I print out the squiggly brackets before and after. This would print out each subset when the time came to process it. Any questions about that? Okay, good. Let me show you one other thing. What if I want to print out permutations, arrangements of things, ordered arrangements, instead of, a subset? How many permutations are there of the numbers 1, 2, and 3? How many permutations are there? What? What? N factorial. In this case, it would be 3 factorial, which would be equal to 6, right? And what are they? Well, it's 1, 2, 3. So, sorry. 1, 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. Does everybody agree those are the 6 permutations of 1, 2, 3? How can I go and do that? Well, I'm going to set up a vector, and in this case, if I want a permutation, I'm going to let my vector be the prefix of the permutation. Suppose I want to build a permutation of size 3, and so far I've put my first one down. What are my choices for the second slot? What is it? 2 and 3? 2, this could either be a 2 or a 3. What is a categorization? How would I categorize what is a candidate for this slot? It's any integer from 1 to n that has not yet appeared in the array. Remember, in a permutation, you can't have a number repeated, right? So if I had a permutation of size 4, and I put down a 2 and a 4, what are the candidates for this spot? It would be the numbers from 1 to 4, okay? Less 2, less 4. My choices here are 1 and 3. Does everybody get that idea? So how would I use this to find what I want? Okay. This is my construct candidates. What am I going to do? First of all, I'm going to check for every integer from 1 to n. Has it appeared in the permutation yet? The answer is so far no. So I set it false. Then I go through the k elements that are already in there and say, well, if a sub I, okay, is, if I is in, if the thing that's in the eighth of ith slot, whatever that value is, it's in the permutation, so I set it to true. Now I've got a Boolean array that will tell me, is I in the permutation or not? What am I now going to do to construct candidates? Go through the numbers 1 through n. If it's not in the permutation yet, I'm going to create a new candidate with the value of I and bop up my collection of candidates. Does everybody see that this logic goes through and finds what are the numbers that are not yet in my permutation? Okay? This is the hard part typically. What else do I have to do to finish up my thing? Well, for process solution, I have to print out my answer. That's pretty easy. Do I have a solution? When I filled my k spots, then I've got a solution. Any questions about that? Okay. Any questions? It's important to be able to trace through what is happening on one of these. Again, if you think about what's happening, you are building, I told you it was like depth first search, it's like you're building a tree, right? What am I doing now? How am I going to find all permutations of length 3? What are my candidates for the first spot? When I'm trying to go through a permutations of length 3, what are my candidates for the first spot? They could be 1, 2, or 3. Does everybody agree? I'm going to put a 1 in there. Now, what are my candidates for the second spot? 2 and 3. And I'm going to put a 2 in there. And what are my candidates for the third spot? And have I now filled my array? Do I now have a solution? Ding, ding, ding. 1, 2, 3 is a solution, right? I went kabunk, kabunk, kabunk. What is my next thing? Now, do I have any other solution here? No. Do I have any other, I bop up to a level. Do I have any other candidate over here? Yes, I do. I have it through, too. What are the candidates for this thing? 3. And what do I get? Ding, ding, ding. I get 1, 3, 2. Do I have any other candidates here? No. Any other candidates here? No. Any other candidates here? Now I can put a 2 in here, right? Now what candidates do I get for this one? What's the candidates for the second slot? 1 and 3. I put in a 1. What are my candidates for the last slot? 3. Ding, ding, ding. I got a solution. No more candidates here. I do have a candidate over here. What candidate do I have now for the last slot? A 1, 2, 3, 1. Ding, ding, ding. Do I have any other candidates here? No. No. Yes. I can now put in a 3 here. If a 3 is a start, what is my candidates now for the second slot? I could have a 1 or a 2. If I put in a 2, a 1, what happens? What's the candidate for the next slot? A 2. Do I have anything else going on? No. 3, 1, 2. Backtrack. Put in a 2. 3, 2. What's the candidate here? A 1, 1. 3, 2, 1. I have no more candidate here, no more candidate here, no more candidate here. I am done. Any questions? Okay. I encourage you all to figure out how the permutations example works. Okay. Any questions? Okay. Let me talk about the backtracking contest. Your homework 4, which is being done individually, is to work on the set cover problem. What is the set cover problem? It is a problem where you are given as input a collection of elements, here you have 12, and a selection of subsets. Here I think I see 3, 4, 5, 6, 7 subsets. And your goal is to cover all the elements, the 12 elements, using the smallest number of input subsets. You see what I mean by subsets? The circular regions. The regions are describing each one of these kind of contains a different subset of elements. Right? Suppose, let's say, you were a collector of, I don't know, what do you guys collect? Okay? Let's say that you wanted to get a collection of books. Okay? And you wanted to get the complete collection of Skinner's books. It's an enviable goal. Okay? What happens if from some guy you could buy books, I have 6 books. 1, 2, 3, 4, 5, 6. Suppose one guy is offering to sell you books 1, 2, and 3 for $1. Somebody else is going to sell you books 2, 5, and 6 for $1. Someone else will tell you book 5. Someone else will sell you book 1 and 6. Someone else will sell you books 2 and 3. Do you kind of get this idea? They're different lots, different packages. And your goal is to get the complete works of Skinner with the smallest number of things that you buy. How many packages would you need to buy in this world? Okay? You would, in this case, I think if I got this book package, and this package, and this package, I've got all of them, right? You may say, but wait, I get 2 copies of, I get 2 copies of book 2. Well, you're lucky, I guess, okay? But you paid for it. But the key was you wanted to buy the smallest number of packages. You could have gotten away buying maybe, if I had each one in its own separate package, maybe you could have gotten away buying 6 packages. You've saved that to 3 packages, right? The set cover problem says, given a collection of subsets that are specified, find the smallest number of them that you can buy such that you will get at least 1 copy of every item.